יופי, good luck, Eli.
אלי, בהצלחה.
Okay, thanks. Okay, so the presentations is titled THD-OPTIMAL staircase modulation of grid-fed multi-point clamp three-phase inverters with active front-end based variable DC ratio supply, which is part of my PhD thesis under the supervision of Professor Alan Kupperman and Professor Raul Rabinovich. Sorry, okay. So this research yielded 5 different Q1 journal papers plus 1 conference paper. So we'll start with some background and motivation. First, why multi-level inverters, or MLIs for short? Multi-level inverters have lower device stress, which means higher voltage ratings, lower harmonic distortion, reduced or completely eliminated output filter size, lower switching frequency operation, which translate into lower power losses, and high power handling. Applications of MLIs include renewable energy source interfacing, variable frequency drives for motor control, and medium and high voltage grid interfaces. Basically, MLI topology may be categorized according to their DC supply requirements. So we have the isolated DC supply, which is used with cascaded H-bridge or CHB for short. As you can see, this, for example, there are 2 modules of CHBs, and the 2 DC voltages are separated. When it's connected to the grid, this is usually the DC supply generation. So it by means of a transformer and a full bridge rectifier and filter. And you have the non-isolated base topology, such as this is called the diode clamped or the neutral clamped inverter. We have this type of NPC, neutral point clamped, and you have this one, which you call the T-type. Basically, both of them may be generally referred to as multi-point clamped or MPC. It's called multi-point clamped. As you can see, the output terminal may be clamped to either one of the voltage potential on the DC bus. Here, the path is very short through 2 transistors. Here, if you want to clamp to the upper voltage rail, you need to turn on all these 4 transistors for this 5-level case. So basically, this one is intended for high voltage. This one is intended for high current applications. Now, when we're talking about multi-level inverters connected to the grid, there are 2 possible scenarios in connecting an MLI to the grid. The first is called grid tied or back-end connection, such as when you have a renewable energy source, either DC or AC, and you are transferring power from the energy source to the inverter and to the grid. You're ejecting power to the grid. The second option is called grid-fed or front-end connection, in which you're using the grid to transfer power via the inverter to a tied load. So this power direction is from grid to the load, and this is the opposite. In this presentation, we are only going to be focused on the grid-fed or grid front-end connection, not on the grid-tied connection. Okay, so these are examples when the CHB, cascaded H-bridge, or multi-point clamp topology are expanded into 3-phase configuration. So as you can see for the 3-phase CHB, this is a single cell, and you cascaded them together per each phase leg. You can see they are connected in series. And notice that you need an isolated, separate DC supply for each cell per each phase leg. Here, you have a common supply, which is made of capacitors connected in series, and this bus serves all 3 phase legs. To generate the DC supply for the CHB, you need an isolated DC supply, which is a complex power stage with indirect connection. Indirect connection simply because it connects via a multi-winding transformer. So we have a primary and secondary transformer. Each secondary transformer has its own full bridge and filter, and you need one of these modules per each module, per each phase, okay? So this one goes with the CHB. For the non-isolated DC supply, the power stage is quite simple. You have direct connection to the grid, no transformer, because the multi-level inverter can handle high voltage ratings. So you have a simple passive multi-level rectifier, a filter, and then you have a passive DC bus made of capacitive voltage divider. Of course, you need to balance these voltages under the operation of the multi-level inverter, and the balancing is handled from the inverter side by implementing a control scheme that measures the voltages and changes the switching state using redundancy switches to maintain a balanced DC bus. However, by the way, clearly, as you can see, because this was much simple, MPC topology are more suited for three-phase application than cascaded edge-based topology. Okay, as for the voltage balancing, it turns out that voltage balancing has its limitations. And these are results which were previously obtained by other authors. So whenever the number of voltage level per phase voltage level indicated by N is greater than 3 levels, with basically most of multi-level inverters, you're going to have some conditions, especially load condition. And by load condition, you can see here, this is the load current. So the load power factor and the fundamental component of the output voltage of MLI, some of their combinations may produce unstable areas in which you cannot maintain a proper voltage balancing. So here's an example of 4-level inverter. These are actual experimental results. These are the 3 partial voltages. Okay, you have a 4-level and 3 partial voltages to make up the 4-level bus. As you can see, they start from a random values, and then they maintain balance within an acceptable amount of ripple. So this is where the MLI is operated in a stable region, and it remains stable. If you operate the same MLI in unstable condition by changing any one of these conditions, as you can see, the voltage, the partial voltages will eventually diverge, and you're going to completely lose the functionality of this inverter. So there are limitations to voltage balancing applied to MPC, which is our motivation to come up with an active solution and grid interface that can supply a balanced DC supply. Okay, quickly review pros and cons of cascaded edge grids and multi-point clamp. So MPCs can be connected directly to the grid. We saw that. Whereas CHB requires a bulky multi-winding transformer plus rectifier per each cell. MPC can attain both odd and even a number of voltage levels N, where CHB can only attain odd N values. This is because of this relation. M represents the number of cells. So as you can see, this can only produce odd numbers. Okay, so let's talk about the second important issue, which is staircase modulation of multi-level inverters, or SCM for short. Basically, there are 2 major switching techniques for multi-level inverters. One is more familiar. This is the high-frequency switching, such as sine PWM or PWM or SPWM, and its alternative space vector modulation, SVM. So this is the concept beyond SVM. I'm not going to get into it. And this is the concept of sine PWM, both of which will result in this type of multi-level and a high-frequency waveform. And the second switching technique is the fundamental switching, or the SCM switch staircase modulation, such as nearest level control, selective harmonic elimination, and most widely used and also most effective, which is the subject of this research, is the optimal minimization of THD, or OMTHD for short. So this is the output waveform for staircase modulation. Basically, staircase modulation was initially designed for cascaded edge grids. As you can see, each cell produces a 3-level voltage, and the composition of all 3 voltage, if you sum them together, you'll get the staircase modulation. So staircase modulation is essentially best choice for CHB. Another motivation for us, you want to use a staircase modulation with MPC topology, because it has a much simpler topology for 3-phase and grid interfaces. and we need to overcome the problems of voltage balancing. Okay, so why SCM and not PWM, especially why we want to apply SCM to multi-point clamp grid-connected inverters. Let's have a look at this, in this case, simulation results. We have 1, 2, 3, 4, 5 levels of phase voltage of PWM, okay? And this is the PWM, and this is the same 5 level of SCM. As you can see, the THD of the phase voltage waveform, short for PTHD means THD applied to phase voltage, is about 27%. And if you switch to SCM, you're going to get a PTHD of only 16%. So this is, from this example for 5 level, there is a relative almost 40% reduction in harmonic distortion. Also, you got much lower commutations, which means lower switching losses. Each level is only used once per quarter wave. Here, each level is used multiple times in high frequency. So lower commutations means lower losses, because the higher the frequency, the higher the switching losses of the transistors. This is some sort of limitation. You need higher filter requirements for SCM, because you all know it is more difficult to filter out lower harmonic content than to filter out high harmonic content. However, when the number of levels is very high, say above 9 levels, then SCM will actually have even lower filtering requirement than PWM. This was proven by Middlebrook and other previous researchers. So why SCM? Let's look at another quick example. This is a 10-level case. So for 10-level PWM, you're going to get 13% PTHD, and for SCM, only nearly 8% phase THD. This time is almost 70% relative reduction in harmonics plus losses. So you can conclude that SCM is the best choice for high-density multi-level inverters. Namely, anything above 6 levels is okay, according to Lipo and other previous researchers. If we take this to the extreme, this is 16-level SCM. Now the PTHD is below 5%, and this is at a turnout point. Notice that when PTHD is below 5%, according to IEEE standard number 518, you no longer need an output filter. You can settle with this voltage without this harmonic without any problem. So this is another advantage for using SCM for high voltage level. So let's talk about optimal minimization to THD, which is the SCM of choice among other SCM approaches. So OMTHD goals are as follows. You want to adjust the fundamental component of the MLI's output voltage, which is represented by the modulation index M sub A. While doing so, you want to minimize the output voltage, or you want to minimize the weighted for motor loads, but we're not going to get into that. This was also part of this research, but I'm not going to deal with weighted THD, only THD. So OMTHD approach is as follows. Obtain optimum phase switching angles alpha. We're going to see what that means. And optionally obtain optimum DC voltage ratios rho by minimizing a cost function, which has a general form of a B-objective problem. So you can see this is the THD expression with its design variable alpha and rho, okay? And you have here the modulation error function, where MT represents the target modulation index that you want. And you have two weights that you need to calculate to properly scale this optimization problem and find the global solution. So this is the general structure of SCM. It can be either with even number of voltage. In that case, rho 0 is different than 0. If it's odd, then rho 0 will be odd. So we have rho 0, then rho 1 times DC, and rho 2, rho K, up to rho M. and you have the alpha 1, alpha 2, alpha 3, and so on. These are the switching angle up to 90 degrees. So you have alpha 1 to alpha m, and they're all between 0 and 90 degrees for the quarter wave. And you have the rows, okay, DC voltage ratio normalized between 0 and 1. So this is the general structure of NCM waveform. So let's talk about applying OM-THD, optimal minimization of THD for three-phase inverters. So this is an assertion, assuming a three-wire three-phase load. By three-wire, I mean that the neutral is unconnected, which is the majority of cases. You only have three wires to connect a load usually. Then it is line voltage THD or LTHD rather than phase voltage THD, PTHD, that should be minimized in three-phase multi-level inverters. Why is that so? Let's look at experimental results. Here we have current THD value measured with FFT-based oscilloscope. This is the modulation depth, modulation index, and the black curve is the current THD values when the multi-level inverter was optimized with OM-THD applied to phase voltage. And the red curve is the same case, but this time OM-THD was optimized while applying the optimization directly to the line voltage, or VAB, or VC, or VCA. As you can see, the difference in current THD are very significant. This is 5 and 13. This is 250% relative. So for all the modulation depth range, you want for three-phase inverters to apply OM-LTHD rather than OM-PTHD. And let's look at quick examples. Phase A, 7 level. This is phase B. Phase C is not relevant right now, and this is the phase AB. So here we did OM-PTHD, and we got a line THD of 10.6%. And here we applied OM-LTHD and got a line THD of only 6.2%, significantly lower. And the waveform looks much more smoother, more sinusoidal than this one. Another aspect that we quickly going to review is applying OM-THD with either with MLIs that have equal or unequal voltage steps, EVS or UVS. So here the modulation depth target was set to 0.4, relatively low. So this is the phase voltage for the EVS, okay, and this is the phase voltage for the UVS, and these are the corresponding line voltages. And these are the optimum results. For EVS, we got, we only calculate the switching angles. This one is constant. And we obtain a THD of 19.2 because this is a very low modulation index. Using UVS, okay, when we allow both the angles as well as the heights to vary. So you can see this is the optimum results for the the switching angles and the DC ratio, and this time the LTHD was significantly lower to 9%. So clearly, whenever applicable, and you can afford it in terms of cost, you do want to use unequal voltage steps and take the full degree of freedom of the optimization. So your design variables are both the alphas and the rows and not just the alphas. Okay, so OM-LTHD basics. Successful OM-LTHD relies on two things. One, accurate LTHD formulation with low computational burden, okay? Second is you want to proper scalarization of the B objective cost function. Namely, you want to select W1 between 0 and 1 and W2 between 0 and 1, so the LTHD expression and the modulation error expression will receive equal prioritization, equal priority, okay? So you want to find the optimum solution. If you don't select W1, W correctly, you're either gonna find non-optimal LTHD higher than the true minimum you can get, or you can get, or you'll get a higher modulation error. So if you're aiming for 0.4, you're going to get 0.42 or something like that. So this needs to be carefully selected. This is a very, very difficult and never done before, because when you change the target modulation index, you need to recalculate W1 and W2. And still nobody have done this before because it's very, very complicated. So the problems are no true closed form analytic LTHD formulation exists in literature. We're going to see why. Second, these scalarization weights are always heuristically or empirically selected, which both of which will lead to suboptimal results, meaning you're going to find a local minima instead of a global minima in most cases. Okay, so what is the real problem with LTHD formulation? So this is the analytical form, generalized for analytical form for THD, which is time-based. So it is dependent on the RMS value, root mean square, and the fundamental component. This is another possible representation called the spectra-based. So for the line voltage, you need to take all odd non-triplet harmonic and count for infinite number of harmonic. Of course, this is impractical. So engineers came up with this H harmonic approximation. Instead of accounting for infinite harmonic, you are stopping at H somewhere. Okay, it could be 3, 5, 25, 100, whatever you choose. So to date, two major approaches to LTHD formulation were documented in literature. First is the numerical spectra-based approximation using this formula. Usually, you're using at least 51 harmonics as per the IEEE standard number 519 recommendation. Still, you're going to be ending up with significant underestimation and consequently suboptimal result. The second approach is called the open form piecewise analytical formulation, which are very computational intensive, will lead also to sensitive and suboptimal results, as we saw in all previously published cases in the last 20 years. So let's understand why. This is phase A, this is phase B, and this is the corresponding phase AB, same here. Here, the three switching, this is a 7-level inverter, there are three switching angles. So here, the third switching angle is relatively small, between 0 and 60 degrees. And here, the third switching angle is slightly higher, between 60 and 90 degrees. Let's look at the corresponding VAB or line voltage waveform. You can see that its max, we have a step up, and here we have a step down. So the line voltage waveform shape heavily depends on the actual phase switching angle values, okay? Which may be step up negative or step down positive, depending on the boundary condition of a switching angle. See, this is different boundary condition. This is the major problem, because if you want to minimize LTHD, you want to calculate to obtain the optimum values of PSA, for example, for equal voltage steps. So you want to obtain this, and you need to formulate the THD expression for the line voltage. However, the line voltage itself is dependent on the actual design variable, which is yet to be known. You can't know them in advance. So what other researchers have done, they use recursive or multiple cases. So let's see, for 3 or 4 number of levels, you only have one switching angles, and you have 3 boundary conditions, either between 0 and 30, 30 and 60 degree, or 60 and 90 degree. By the way, the 30 degree segmentation is related to the fact that line voltage leads phase voltage waveform by 30 degrees. Sorry. For 5 and 6, you're going to have 6 boundary condition, because you have now 1 extra switching angle. For 7 and 8, you're going to have 10. This is the general permutations pieces, where this funny brackets indicates the floor operator. So the problem is that that the piecewise LTHD formulation consists of different LTHD expression for each boundary condition. You need a different complicated expression for each boundary condition. Therefore, global search algorithms used to find the optimum value must use all pieces and search for the optimum solution within all boundary conditions, which significantly increases the computational burden. And the more it's complicated, it's not a matter of taking more runtime. That's not a problem, because you do it offline anyway. The more it is complicated, it's more prone to errors. You're going to find non-true global optimum values. And this was proven as well. So let's have a look at previously proposed LTHD formulation. Here, in this case, you can see that clearly they use the H approximation with the 200 harmonics. Okay, so this was a numerical approach. Here, the authors have declared that an accurate closed form expression was obtained for LTHD. However, if you look at the expression, you can see that the integral for the RMS remains unevaluated. Okay, so they propose a graphical approach to evaluate. So you need to calculate this term and plug it in here to find the THD. So this is misleading. This is clearly a misuse of the term closed form and from mathematical formality. This is actually an open form, not a closed form. And this, you can see there are two alphas and many boundary conditions. So this is a simple 5-level inverter. As you can see, for each boundary condition, they had to come up with different complicated expression. By the way, for some reason, they managed to reach total of 9 terms because they exceeded behind 90% up to 90 degrees up to 100. So 3 terms here are completely redundant. We've checked, they are simply the same expression repeated three more times again and again. Anyway, so this is a problematic piecewise formulation. As for OM-LTHD approaches, as you can see, these authors here use numerical approach with 101 and empirically selected coefficients, okay? These authors decided to set W1 to 10 and W1 to 1, justifying this heuristically selected scalarization weight as the output THD of the discussed inverter is mostly above 10%, which is incorrect, unfortunately. This inverter can reach anywhere between 6% and 150%. So choosing specific value for the weights maybe going to give you good results for a specific target modulation index, but not for the rest. And so this one was heuristically selected scalarization weight. And finally, this is we were very shocked to see this. This was published in the IET journal. As you can see, something is very wrong here. This is the fitness function. So you may say they chose W1 and W2 to be equal to 1, but that's not the case. They completely overlooked the issue of scalarization, and this specific research have yielded completely invalid results. So this is the screen capture of the empirical scalarization. It's supposed to be somewhere like this, very smooth and analytical. See, there are a lot of fluctuations and sensitive results. And these are the no scalarization results. This is the no scalarization results for equal voltage steps. And this, unfortunately, for the unequal voltage step, this is completely noise. And also the modulation error is very large. So these results are completely invalid. Still, it was somehow published and cited many times. So the problem with traditional OM-THD. So if you take all these results and do a digital extraction and put them all together, so these were published in the IEEE transaction on industrial electronics back in 2010. This was published in the IET Power Electronics and Journal in 2012. And this is our results, okay? Just a preview. As you can see, the dashed line is very analytical in nature. And of course, the values are much lower and the modulation error are kept below a certain value that we define. Well, I will get into that later. So let's quickly see our review our research objective. So we want to derive a generic closed form LTHD expression to be used for OM-LTHD. We want to completely eliminate the need of cost function scalarization, okay, to improve the OM-LTHD results. And we want to develop an active front-end solution with power factor correction to allow implementation of OM-THD-based SCM to grid-fed 3-phase multi-point clamp MLIs. This is the system that we propose. This is the grid. This is the new topology called the negative multi-level rectifier. This is just a coupling filter, and this is an existing multi-level inverter, and all of which are jointly controlled to provide a minimum line voltage THD for any target output voltages. So the proposed LTHD formulation, let's consider a generic cascaded H-bridge phase leg here, and its MPC equivalent here, and let's assume that its output voltage is a normalized, and it has a quarter wave odd symmetry. Okay, so these are the alphas here. Okay, and this is the rows, the heights. Okay, so this is a very generalized quarter wave SCM or staircase signal for phase voltage. The total number of voltage step per quarter wave, excluding the zeroth step, which is only relevant for even values of n, can be formulated as follows. By using the floor operator, and we can unify both cases into one. Okay, so these are the parameters here. And this just makes sure that the voltage steps are normalized and weighted, where the FT represent a parity toggle function. This way we can combine both odd and even values of n into a single expression for simplicity. If we are discussing equal voltage steps, then clearly row 1 and row 2 and all will equal to each other, and it should be made equal to this expression here, where n is the number of voltage levels. Okay, so our proposal. We're going to do this very quickly. The generic normalized phase voltage waveform can be expressed using a summation of shifted and scaled unit step function, Heaviside function. This is the VA of theta. You can see this summation from K1 up to M of rho K scale, just scaling and shifting the unit step function. This is an optional, okay? This is the toggle function for even or odd values. And this is the definition of the Heaviside function or the unit step function. Using this, it is possible to come up with a fundamental component, all the line voltage modulation index. I'm not going to get to that, but you can formulate the modulation component as well, modulation index component. Okay, which by the way, it's between 0 and 1.1%. When it gets a value of 1, it indicates a sinusoidal, true sinusoidal. So this is over modulation and this is under modulation. This is the range. Okay, so now let's discuss the line voltage waveform. So line voltage waveform, VAB, is defined VA minus VB, where VB is simply VA shifted by 120 degrees. We know that. Now shifting VAB by minus 30 degrees, utilizing periodic function properties. We all know this one here. After some extensive manipulation and simplification, we can formulate VAB to be recentered as a quarter wave function with odd symmetry, valid for any value of n. This is, as you can, it is defined across 3 segments as expected: 0 to 30, 30 to 60, and 60 to 90 degrees. Okay, where VA is the step function based phase voltage SCM formulation. Now, recalling the time domain THD is given as follows. We all already know what is MA. We came up with an expression. All we need to know is to formulate the RMS square, normalized RMS square. So the normal RMS square is given as follows for a symmetrical function, assuming theta is in degrees. So let's collect terms. Use the VA. We plug it into the VAB, and we plug VAB into the RMS square function. Now we have the power of 2, which is problematic with the summation. So we use the distributivity rule to convert a sum of squares to double summation. Still, we are stuck. The biggest challenge is how do we symbolically evaluate a parametric integration over a product of unit step function? This is the main problem. We could not find any solution in mathematical textbooks, so we need to come up with our own. Luckily, I just bumped into a formula I found in Wikipedia. So it turns out that the unit step function can be represented as a derivative of the max operator. Okay, as you can see here, max theta minus alpha and 0, the maximum. You take the derivative, you get unit step function shifted as alpha. Also, another identity can be found at MathWorks is that minimum xy can be converted to maximum xy and vice versa. This is similar to the conversion, reciprocal conversion of the unit step function. So we can utilize these 2 properties, and after extensive manipulation, we can come up with a generalized symbolic formulation for applying a definite integral over a product of 2 shifted step function, Heaviside function. And this is the solution, min and max. So you can utilize this, this identity to the VRMS expression, and after some simplification, we end up with this final solution. So this is LTHD. In modulation index is already given here, and these three nominators are given as follows. As you can see, this is just functions of min and max operators, and they contain the switching angles and the DC ratio values normalized and in degrees, and we managed to completely eliminate the integral, and this LTHD formulation is valid for any number of levels, whether odd or even in both equal voltage steps and unequal voltage. So this is a true generalized formulation, never before proposed in literature. So let's look at quickly at the formulation results. This is the number of levels 3, 4, and 5, and this is the input phase switching angles. Let's focus on 5. As you can see, we can obtain symbolical, so a mathematically exact solution. If we convert it to numerical, we get 9.4%. Comparing to results obtained using numerical approaches with 51 harmonics, as you can see, there is a significant underestimation. Is an example for unequal voltage steps for 11 levels. We plug it in, this is what we get. So if you want, you can leave it like that, most accurate, or you can convert it to numerical with infinite number of digit after the dot. So LTHD formulation that we perform yields mathematically exact symbolic result for any arbitrary value of n, which is never before proposed. So let's talk about the proposed optimal minimization and LTHD. So as an alternative to the traditional B-objective function, we propose a simple single objective function with additional constraints, okay? So this is what we propose. We need to minimize LTHD, okay? And as a parameter, alpha and rho are the design variable subject to this constraint. The first three constraints simply set the domain for the design variable. They're not very important. The third constraint set the modulation error requirement. So epsilon t is the desired tolerable modulation error, ME, and epsilon a is the actual ME value defined as follows, where MT is the target modulation index, and then MA we already defined here. So this is the OM LTHD formulation, which is solved using MATLAB or if Maple, you can solve symbolically or numerically, which again, first ever proposed solution. Okay, so let's continue and look at results. Okay, we're close to the finish. So these are unequal voltage step results. This is the minimum THD for different values of a number of levels from 7 to 13 as a function not of the target modulation, at the actual modulation. So we want to make sure that we do get the correct result. This is the corresponding percent modulation error. When we run the OMTHD problem, we set the epsilon t, the target modulation, to a maximum of 1%. As you can see, the results are never exceeds 1%. They're either below 1% or above 1%. These are optimum switching angles for 7-level case. The black ones are our results, and the red one our results proposed elsewhere. And this is the corresponding THD. This is phase voltage THD, and this is line voltage THD. Once again, you can see that our results are lower, and they do not contain any sensitive or fluctuation as with previous results because of this truly analytical formulation of both LTHD and OM LTHD problem. This is an interesting. The blue axis represent the actual modulation error in percent, and the red axis the corresponding LTHD. So we run for different modulation index value, we run the optimization twice. Once we set the target, the maximum tolerable error to 5%, and this is, you can see that the result always remain below 5%. And once we run this, repeat the optimization, this time with 0.5% here. And these are the corresponding minimum THD. As you can see, LTHD, when the target modulation error is allowed to reach 5%, will be much lower than if we strict the modulation error to 0.5%. So our proposal allows the user to choose whether he wants higher modulation accuracy or better harmonic performance as he wishes. So the target modulation error can be set to virtually any value, even zero. You can, if you set it to zero, you're going to get LTHD, not the lowest, but still quite good results. So these are results. This is the screen capture of a published paper. And as you can see, this is exactly the same. This is a digital extraction of this. So this is 15, this is 15. So this is 1:1 digital extraction. So this was published in IT Power Electronics Journal back in 2012, okay? And this is their result, and we are comparing them to our result. This is the corresponding modulation error. Our modulation error remains below 1%. Their modulation error here, which is 20%. So basically, these results, unfortunately, are virtually invalid. And this is another proposed approach called the optimal hybrid modulation. Not only that we adjust the switching angles and the DC ratio, we also allow to adjust the total DC voltage. So this helps us get even lower LTHD formulation, which is possible with the back-to-back connection of the multi-level rectifier and inverter solution. Okay, so finally, let's talk about the proposed active multi-level front end. Okay, so if you consider the well-adopted Vienna rectifier, which is a 3-level active front-end solution with power factor correction, this is its topology. These voltages represent the grid voltages. We have 3 input inductors, just like in a DC-DC boost converter. We have a simple full bridge rectifier and 3 bidirectional active switches realized by 2 transistors. This is the total DC voltage. So the absolute value, instantaneous absolute value of the grid can be controlled by the active switches. If you turn switch on, it will increase, turn it off, it will decrease. The total DC voltage can be indirectly controlled by simply controlling the magnitude of the grid currents. And finally, the error or the balancing can be controlled by controlling the DC offset of the grid voltage. So everything can be controlled by proper PWM to these active switches. For the Vienna rectifier, this is an existing solution. And so let's talk about the controller of Vienna rectifier, which serves as the basic concept for our controller of our multi-level rectifier. So we sample the grid voltages, we sample the 3 grid currents, we sample the 2 partial voltages, and we sample the DC reference. We calculate the total DC error. It is fed to a PI controller, then it is multiplied by the shape of the phase voltages. Simultaneously, we take the error of the balancing, we feed it to a second PI controller when we add the result to this signal, and this will result in the reference of the grid currents. We take the absolute value of the reference current and the actual measured currents, and we feed them to the modulator, and we create the PWM signal for the active switches. So we want to convert the Vienna rectifier, expand it to the new multi-level rectifier, which naturally we call it Negev rectifier, okay, because Ben-Gurion University of the Negev. So the goal is we want to increase the DC link voltage levels from 3 to N, while fully preserving the front-end power factor correction capability of the Vienna rectifier and allowing both balanced and unbalanced DC link generation. So this is the construction of the DC bus for multi-level inverter. So we have the row 0, and you have row 1 upper, row 1 lower, row 2, or generally row K and row K up to row M and row M. So we need to generate quasi-symmetric DC bus with this MLR. So let's look at the Vienna rectifier to Negev rectifier evolution. This is the 3-level Vienna. By adding, by adding 3 more switches or a switch cell and 1 capacitor, we end up with 4 level. And this is a 5-level, 6-level, 7-level. This is the evolution up to 8 levels. So we have total of n-1, n the number of levels, n-1 switch cells, a total of 6 times that of IGBTs, n-1 capacitor for our topology. So this is the generalized topology, and this is the per phase logical schematic. So if SM is turned on, we increase the absolute value of the current, and then SJ will kick in to select to which junction we want to route the current so we can maintain the balanced voltage as we want. to do the partial voltage balancing, let's look a quick snapshot of a 5-level case. So here we have phase A, phase B positive, and phase C negative. Now suppose that we turn these 3 switches on. We can only turn 3 switches at a time, 1 per phase. We're going to force the current to flow upward V3, which will cause V3 to drop, okay, to decrease. Similarly, if we use a different set, for example, of a switch sequence, we're going to cause the current to flow downward V3, and therefore V3 will charge. The problem is that we have 1, 2, K up to N minus 1 partial voltages that we need to balance, but we only have 3 switches that we can turn on at any given time. So we can only compensate or correct 1 partial voltage at a time. So this is the problem. We can't correct them all at the same time. So what we propose, we simply borrowed a telecommunication approach, which is called, maybe you are familiar with, time division multiplexing. So the MLR controller is virtually identical to the Vienna, with only added time division multiplexing critical error compensation, we call the TDM-CEC block, plus a DCR divider block. So this is the virtually identical control block of the Vienna, and we have included 2 extra blocks. The first one simply takes the partial voltages and divides them by the required DC normalized DC voltage ratios to get the unbalance that we want at the output. The TDM-CEC block will analyze, measure all voltages, create a set of errors, and determine which error is at critical state. By critical state means that its absolute value is at maximum. According to that decision, it will turn the proper set of switches to effectively correct that specific error. So let's just jump for a quick, this is an example for 7-level MLR, so n equals 7, and the number of errors to be compensated are 6. So the first constraint is the total DC bus, which is handled by the external loop with the PI controller. You want sum of all partial voltages to follow the DC reference. You have the external error, V6 minus V1. You cannot correct it with the switches because it's connected to diodes. And this one is corrected by the second PI controller, exactly like the Vienna rectifier we just saw. And we have the remaining of the errors. So we take averages and we subtract each one of these middle partial voltages. For example, let's focus on V3 quickly. So suppose you want to increase V3. What do? We measure all grid currents, and we determine which one is positive, flowing toward the bus, and negative, flowing toward the grid. And we simply direct all positive currents to the upper junction and all negative currents to the lower junction, causing V3 to increase and correct this error. Suppose that this error is the critical one. If we want to decrease V3, we simply do the opposite. Direct negative currents to the upper junction and positive to the lower junction. And we do this each sample time for the specifically the currently critical error. Eventually it's going to correct itself. So finally, this is the MLR to MLI back-to-back connection. This is the multi-level rectifier. This is the interface filter, and this is multi-level inverter, which is a realization of this proposed. So let's now look at quickly at results. So this is simulation results. We start with simulation, then we go to experimental. This is simulation result of LTHD-OPTIMAL 7-level MLI with equal voltage steps set to 1200 volt. Notice that the 6 partial voltages are set exactly at 200 volt. The ripple is quite neglectable, plus minus 1 volt. The input currents are sinusoidal following the grid voltages, and this is the output voltage of the multi-level MLIs. THD remained at minimum according to switching angles. As you can see, the ripple is quite small, and this is unequal voltage step with optimal hybrid modulation. This is the VFD variable frequency drive emulation, 1200 volts. At the time t equals 0.3, we have a change. The output frequency of the inverter changed from 50 Hertz to 80 Hertz, while the modulation depth changed from 0.8 to 0.5. These are the value set for the optimum THD in this region for the partial voltages, and this is the total DC, which is set to 1200 volt, and then we change everything. You see 200 becomes 271. Again, these are calculated to obtain minimum THD. Now the total DC bus is changed to 1200 volts. And as you can see, before the change, currents are sinusoidal in phase with the voltages, and so after the change. And what the most important thing is that even at 80 hertz, quite fast, the transition time takes only 2 grid cycles, which is very excellent to any power factor correction grid interface. Now, quickly, experimental results were based on controller per hardware in the loop. So here we have the setup, this is the scope, this is the host computer. We have the Hill 402 Typhoon Hill, the MCU, Delfino Texas Instrument, and the DSP host card. And these are results for 8 level with the modulation depth set to 0.8, EVS and UVS. As you can see, the measured THD do follow the theoretical result. We have UVS lower than EVS. This is for phase voltage THD, and this is for line voltage, the EVS and UVS. And finally, one last experimental result, 4-level MLR, MLI with UVS and OHM, 1200 volt, phase voltages, corresponding current voltages. As you can see, there are basically power factor is 1 ohmic. These are the 3 partial voltages and measured THDs, and this is the input, by the way, is 50 hertz and the output is 60 hertz. So it also does a frequency conversion, and these are the line voltages of the 4-level MLR. The line voltage will have a total of 7 voltage steps. And conclusions quickly. So a first ever successful generic N-level closed form LTHD formulation was derived and verified. LTHD formulation was utilized for unequal voltage step based OM-LTHD, which allow restriction of the modulation error. This is the most important, to any desired value. A novel active multi-level rectifier designed to serve as front-end solution for staircase modulation-based multi-level inverter was developed and verified. Finally, LTHD-OPTIMAL hybrid modulation, grid-fed MLR, MLI back-to-back power conversion system was introduced and verified. By the way, it calls hybrid because the multi-level rectifier operated at PWM, while the inverter is operated with SCM. And so that's it. Okay, so if you have any questions, I'll be happy to answer.
Okay, thank you very